In this programming example, I will show you how you can use PyTorch to improve the digital classification network example that we have implemented in previous video. Most of the code is the same as the previous programming example, and we will do some changes both for the network as well as the training process. For example, here I'm using batch size of 64 instead of 1. So here we are declaring a batch size to use the parallel computation instead of using just one example. And the actual network uses activation function for the first layer to use ReLU instead of tanh. And we are also going to use the softmax activation function in the last layer. But in PyTorch, to implement that, the actual function is included in the loss function itself. So we only need to declare a linear layer here, and then by changing to use this cross entropy loss function layer, that will also include the activation for the last layer. Then we are here just retrieving those two layers. We do that just to use layer 1 and then layer 3. So layer 1 refers to the first linear layer here. And there we will use something called k-mean initialization. This is the same as hey initialization that we talked about before. And then we set the bias weight to be 0. And for the second layer, the output layer, we will use Zephyr uniform, which is the same thing as Glorot initialization. So we do that for the regular weights, and then we set the bias weight to be 0. Now we have created the network. Let's look at the training process. We will use Adam optimizer instead of stochastic gradient descent. And we don't need to provide a learning rate. We will just use the default training rate for the Adam to start with. And here we will use the cross entropy loss for as the loss function instead of the mean squared error. We no longer actually have to compute the one-hot encoded version of the targets because the loss function, which is the cross entropy loss, the loss function here, is assuming that it gets the index rather than the one-hot version. So we can just give the targets here and compare to the outputs directly. So we have the indices and the targets, and it will be an array of 64 elements in parallel. And we do this equal operation. We will check element-wise if these are equal or not. Then we sum up. So this will give us out of these 64 examples for how many is the output equal to the label. So given that we are running 64 examples in parallel, instead of one at a time, the training process will be really faster. And I run this so you can not wait until the process is ended. So you will see that each epoch goes significantly faster than what we did in previous programming example. And not only did the training go faster than before, but also it is a better result. So the training accuracy is about 98% and the test accuracy about 96% compared to what we had previously, 95% and 94% respectively. So the running multiple training examples in parallel made things faster, and then changing the network and using Adam optimizer made the network doing better in terms of accuracy.